Hello, Honored Pre-Calculus. This is day 4 of our limits notes, specifically on continuity. All right, this is going to be the easiest notes day ever. All right, so continuous. You already know what continuous means. It means something that goes on forever and doesn't stop, right? So in official math language, it says that a function is continuous if the limit from the left equals the limit from the right and that there actually is a closed dot where they meet. And in this example, they're going to meet at x equals a, right? So that would be like right here, here would be a, and we would be saying that the limit from the left, so as we're coming towards a from this way, it happens equal the limit from the right coming at it from this way, and it meets at exactly this point in between. That's it, that's continuous, pretty easy, right? Okay, so in your own words, I would say what is continuous? Continuous is if a function can be drawn without lifting your pencil. Right? So anything that you could draw that goes like this or that goes like this, doesn't matter what it is, as long as whatever it is that you draw, you can draw without lifting your pencil, then it's going to be continuous. Super simple, right? All right. So the next part says that if you have a limit as x approaches a from the left and it equals a dot, then f is continuous from the. Okay, let's go and look at this picture and see what the heck they're talking about. All right, so I'm going to assume this is where we're talking about on A. And we know from our limits from our notes before that I can either be on the roadway approaching A from the left or from the right. They are telling me to approach from the left. And they are saying that it has to have a closed dot. Okay, and then I can say it's at least, ooh, I should have put that up here. Okay, so from the left, closed dot. So if you're not going to talk about the whole function, you're going to piecemeal it and say this section is continuous, then it has to end with a closed dot. So this part is a yes. This part over here is a no, and it's a no because of the open dot. Okay, so I can say that this is continuous coming towards A from the left, but I can't say it's continuous from the right. So this one is continuous from the left. Okay, at the same time, here is a different picture. Okay, and this time they are saying from the right. They think it's continuous, so let's go see. So here is A, and from the right, meaning if I travel this way from the right towards the left, it will end at a closed dot. That's happy face, that's good. That is continuous from the right. On the left, it looks like it's going to go up forever, so that is a sad face. Okay, so this one is continuous from the right. Okay, all right, so we can say an entire function is continuous. If all the way from left to right, it's continuous and you didn't have to pick up your pen, but we can also say sections of it are continuous as long as it ends in a closed point. Okay, now there are 3 different types, so like subcategories of discontinuities. So there's 3 different types of them. And they kind of fall under 2 different words, kind of a generic word and then our everyday word that we talk about things. So let's talk about our everyday words first. Okay, so a jump discontinuity is one where if you are traveling from left to right, and I'm drawing my little stick figure dude who is traveling from left to right, and he's traveling from left to right, and then what happens? Well, once he gets here, he has to kind of jump and go down onto this one over here. Right? Okay, so he had to do a jump. Okay, so we call that a jump discontinuity. Okay, the next one, let's go see. We've already had experience with this one, right? So here I am walking along my graph, here I am walking along my graph, here I am walking along my graph, and then what happens? I hit a hole. This one is called a hole discontinuity, right? Somewhere on the graph where there's just one point that doesn't exist. Now it could have a closed dot somewhere else, or it might not have a closed dot anywhere else, but it's one where I would just have to go over the hole and I would be fine. Okay, and then our last one over here, this one has asymptotes, right? So asymptotes, right, are vertical asymptotes where the graph keeps getting towards it but never actually gets there. So again, if I'm my little stick figure dude and I'm walking this way and I'm walking this way, there is no way I'm ever going to end up back on this side unless I turn into a different person completely and then start walking over on this side, right? There is no way that this happens. Okay, so there is no way that that happens. So those are called asymptote discontinuities. All right, so those are our everyday words for those. You kind of say what's happening. There's a jump there, there's a hole there, there's an asymptote there. But they also have just generic type of names to them. Okay, so there's removable and non-removable. So the only one that's removable, is a hole, because it's kind of like if you were just going to come along and you had this little patch, right? And you were going to move it onto the hole and patch it. So if I just plug up that little hole with that little light blue dot, it's fixed. Okay, so we call that a removable discontinuity because it's super easy to fix. You just plug the hole. The other two, though, are considered not as easy to fix. So these are non-removable discontinuities. And then we have one other word for asymptote discontinuities, and that is infinite. And why is it called infinite? Well, of course, because the vertical asymptotes go on for infinity. Okay, so they all have several different names. Most of the time we will not care if you use just the everyday language for them, the jump, the hold, the asymptote, or infinite discontinuities. All right, you guys, that was it. 7 minutes, not bad. All right, bye.